Okay, Assalamualaikum warahmatullahi wabarakatuh, and welcome everyone to our presentation on the comparison of sensor placement in wearable system for measuring plantar flexion and dorsiflexion gait parameter. I'm Abdul Hadi Abdul Razak, and I'm honored to present our collaborative work today. This research focused on developing an innovative wearable sensor system to enhance the accuracy and reliability of gait analysis, particularly in capturing the intricate movement of plantar flexion and dorsiflexion. Okay, straight to introduction. Gait analysis is crucial for understanding human movement pattern, assessing musculoskeletal condition, and enhancing rehabilitation and sport performance. This study aims to address the challenges in accurately measuring plantar flexion and dorsiflexion angles. Traditional gait analysis system often required extensive lab setup with expensive equipment, which limits their accessibility and practicality. By developing a wearable solution, we aim to make gait analysis more accessible and applicable in real-world scenario, providing valuable insight for clinical and athletic use. Okay, gait analysis is a systematic examination of the way in which a person walks. A gait analysis is performed by gait disorder involve aberrant walking pattern that can be caused by disease or injuries. As a result, this analysis can assist in determining the source of patient pain while standing or walking. Plantar flexion is the movement of ankle joint that causes the toe to point down away from the shin, while dorsiflexion refers to the opposite movement, where the ankle joint bends upward, bring the toes closer to the shin. A current gait analysis system are often limited in lab setting, which restrict real-world application. Moreover, wearable technology sometimes show inconsistencies, and there is a lack of clear guidelines on sensor placement affecting data reliability. Laboratory settings do not represent the typical environment where gait pattern occur, such as in daily activities or athletic performance. The inconsistency in wearable technology data output can result from various factors, including sensor placement, calibration issues, and individual differences in gait mechanics. Establishing standardized guidelines for sensor placement is essential to improve the accuracy and reproducibility of gait measurement. So we divide into three main areas: design, a wearable device using the Node MCU microcontroller for effective monitoring and plantar flexion and dorsiflexion gait parameter. This includes ensuring the device is lightweight, comfortable, and unobstructive for the user. While for the accuracy, is a device that consistently measures data in line with theoretical values, minimizing discrepancies and enhancing the reliability of measurement. And the placement, what we target to is to the optimal placement of the wearable sensor for precise data collection. This involves testing various positions on foot and ankle to identify the most accurate and consistent placement. Our focus on developing a practical, accurate, and user-friendly device. The Node MCU microcontroller was chosen for its versatility and ease of integration with various sensors. Ensuring consistency with theoretical values is critical for the device reliability. Lastly, determining the optimal sensor placement will maximize data accuracy, enhancing the device utility in different applications. So this is the methodology that we use in our work. So our system utilizes the following component. For the hardware use, we use a Node MCU microcontroller, ESP8266. This is act as the central processing unit for data collection and transmission. We use lithium polymer battery, which provide a compact and reliable power source for the wearable device. And lastly, the IMU sensor, MPU6050, velocity and of the foot capturing detailed movement data. The Node MCU microcontroller is a popular choice for IoT project due to its built-in Wi-Fi capabilities, which facilitate data transmission to mobile device or cloud storage. The LiPo battery ensure long-lasting power supply, essential for continuous monitoring. The MPU 6050 sensor combines a gyroscope and accelerometer, providing comprehensive motion data critical for accurate gait analysis. While for the software use, we use Arduino IDE used for programming the Node MCU microcontroller. It provides a versatility and user-friendly platform for developing and uploading the control code. And we use Blink app also for the software to facilitate real-time data visualization and user interaction. The apps allow user to monitor gait parameter directly from smartphone, providing immediate feedback and analysis. The Arduino IDE offer a robust platform for coding and testing the microcontroller. Its extensive library support simplifies the integration of various components. The Blink app allows users to monitor and interact with the device in real time, making it user-friendly and accessible for both clinician and patient. Okay, this is the flow chart. The system operation involves several key steps. First, circuit connection, establishing the connection between Node MCU and the IMU sensor, ensuring proper communication and data transfer. Soldering, assemble the hardware component securely to create a durable and a reliable device. Then we calibration, initialization, and calibrating the sensor to ensure accurate measurement. Next, data collection, capturing movement of the data during gait analysis. Data visualization using the Blink apps to display the collected data in real time. This process ensures that each component of the system function correctly and contribute to accurate and reliable data collection. Okay, our experimental setup involves a subject walking 15-meter pathway with a wearable sensor placed in two different locations. The tarsal region, ankle, near the ankle joint, and the metatarsal region between the bridge and the foot of the toe. This is the two different locations that we are testing, which is more suitable for this gait parameter, to capture the gait parameter. Each subject was introduced to maintain their balance to ensure accurate calibration. This setup allows us to compare the data collected from two sensor placement and determine the most effective location for accurate gait measurement. So from the table there, I mentioned we did some literature that for a normal gait healthy people, the Plantarflexion is in the range of 40 to 55, and Dorsiflexion is the range of 10 to 20 degrees. Okay, for result and discussion, firstly we looked at the dorsiflexion. We observed dorsiflexion angles for both tarsal and metatarsal placement. The data showed that the tarsal placement provide more accurate and consistent measurement compared to the metatarsal placement. This finding suggests that the tarsal region is more stable and reliable position for capturing dorsiflexion movement. And here is for the measurement that we did for the plantarflexion. Similarly, we measured plantarflexion angles and found that the tarsal placement again provide more accurate data compared to the metatarsal placement. This consistency across both types of movement highlight the tarsal region as the optimal sensor placement for comprehensive gait analysis. Okay, for comparison data, we compare the measure angle with theoretical values. The tarsal for plantarflexion, tarsal is when we did the experiment, is around 44 to 60 degrees, while the metatarsal is 59 to 73 degrees. So based on the theoretical, 45 to 55 is the region that is more accurate if we put at the range angle at the tarsal area. While the dorsiflexion tarsal measurement is between 9 degrees to 20 degrees, metatarsal is 2 to 10 degrees, theoretical is 10 to 20 degrees. So this comparison indicate that while both placement provide valuable data, the tarsal region align more closely to the theoretical values, making it preferred sensor location. So as a conclusion, our wearable sensor system represent a significant advancement in gait analysis technology by identifying the tarsal region as the optimal placement for the sensor. We can provide more accurate and reliable data for various applications in biomechanics, rehabilitation, and sport science. The user-friendly interface and real-time data visualization through Blink apps empowered users to make informed decisions about their gait pattern and ankle joint health. Okay, for further recommendation, to further enhance our system, we propose that we categorize into 3 parts. Enhance sensor integration, incorporate additional sensors such as bend sensor to capture more detailed movement data and improve overall accuracy. For clinical validation, conduct extensive clinical trials with larger and more diverse population to validate the system accuracy and reliability. And lastly, data management to develop advanced method for storing and transmitting collected data, enabling further and enhancing the capabilities of wearable device for gait analysis. Okay, before we end, I would like to acknowledge we express our gratitude to UiTM RMC for supporting this project through PYPB incentive. We also thank the School of Electrical Engineering, College of Engineering, UiTM, for providing the necessary lab space and equipment. Your support and resources are invaluable to the success of this research. And with that, I would like to end my presentation. Thank you for your attention. I'm open for any question or further discussion on this topic. Your feedback and insight are greatly appreciated as we continue to develop and refine our wearables sensor system for gait analysis. Assalamualaikum warahmatullahi wabarakatuh.